Bioinformatics Micromodules, Properties of Burrows-Wheeler Transform. In this module, we explain some properties of BWT to build up our knowledge such that finally we can study how we can do text search using it. Let's first recap the definition of BWT, which is the last column of the sorted rotation matrix. For example, given the input sequence S, which is $, we list all the rotations of it as different rows of a matrix, sort them lexicographically, and then take the last column of it as the output of BWT, which we denote as B. There are several things that we want to learn about BWT. The first thing is how B can be constructed from S conceptually, which we just talked about. The second thing is how we can construct B from S efficiently without materializing all the rotations and sorting them. And we have already covered this topic in the last module. Next, we are going to talk about some additional properties of the sorted rotations. After that, we will explain how we can get back S from B conceptually. And by conceptually, again, we mean a method that is relatively easy to understand, but computationally inefficient. After that, we will talk about an alternative method for getting back S from B that is much more efficient. Finally, using the knowledge related to these first 5 topics, we will be able to study how B can be used to search for particular subsequences from S. In this module, we will focus on topics 3 and 4. Now, let's study some properties of the sorted rotations. We will start with some simple properties to get warmed up. The first property is that the rotations in different rows of the sorted rotation matrix are all different. Why is that? This is because of the end of sequence symbol $. There is only one $sign symbol in S, and each rotation places it at a different position, and therefore all rotations must be different from each other. If you agree that this property is true, then the second property is probably obvious to you, that every column in the sorted rotation matrix has the whole set of characters originally in S. For example, if we count the frequencies of different characters in S, we find that it contains $1, 4 A's, 1 C, 1 G, and 4 T's. In every column of the sorted rotation matrix, we also have this same composition of characters. Why is that? This is because in the sorted rotation matrix, for each column, each rotation contributes the character originally from a different position of S. If you have difficulty understanding it, just think about the original matrix of rotations before sorting, which has the position shifted by 1 in every next row. In that matrix, it is clear that each column has the same composition of characters. Then, when the rotation matrix is sorted, no matter how the rows are swapped, the composition of characters in each column is never changed, and therefore this second property remains true. After the warm-up, let's study a less trivial property now. This third property states that different occurrences of a character tend to be clustered together in B. For example, in S, the 4 A's are all not adjacent to each other, and the 4 T's are also distributed across the whole sequence. However, after transforming S to B, we see that 3 of the A's are adjacent to each other, and so are 3 of the T's. To see why, we should notice that there are some subsequences that repeatedly appear multiple times in S. For example, the subsequence TA appears 3 times in S, at positions 1, 3, and 8, respectively. Let's consider the A and the T in this pattern separately. When the rotations are sorted, those starting with A must be next to each other. Among the 4 rotations starting with A, 3 of them are due to this TA pattern, and therefore these rotations will have the T in the last column. In other words, due to the A of this pattern, these rotations are placed close to each other after sorting, and as a result, their T's in the pattern are also placed close to each other in the last column, which creates the clustering phenomenon described by this third property of the sorted rotations. In our example here, the pattern TA is only 2 characters long. If a repeating subsequence is longer, say with 10 characters, it would create an even stronger clustering effect because there is a high chance that the rotations that start with the last 9 characters of the pattern are all adjacent to each other after sorting, since it is not easy to have these 9 characters outside the pattern by chance. What is the significance of this clustering? One significance is that after performing BWT, the resulting sequence can be more easily compressed by methods such as run-length encoding, which records a run of the same character by only the character and the number of occurrences, rather than explicitly listing each occurrence one by one. Although data compression is not our main focus here, this third property of the sorted rotations is also something interesting that can help us understand BWT more in general. We now study another interesting property of the sorted rotations, which is getting S back from B. Before discussing how this can be done, we should first discuss the invertibility of BWT. In other words, given a sequence B, is it always possible to get a sequence S such that B is the BWT of S? And when such an S exists, is there always only one S that produces B by applying BWT to it? Although we are not going to give a formal proof here, as we discuss a conceptual method for getting S from B in a moment, we will see that if B is indeed the BWT of a certain sequence, we can always get back that sequence uniquely from B. This conceptual method works like this. First, we create an empty matrix and add B as a column of it. Then we sort the rows of the matrix, and after sorting, insert B as the new first column of the matrix. This is repeated until the matrix contains n columns, at which point we extract the sequence in the first row, move the $ symbol back to the end, and the result is exactly S. Don't worry if this procedure sounds complex to you. Let's see an illustration, and you will understand exactly how it works. Suppose we have a sequence B, which is GTTT-CAAA-T$8, produced by applying BWT to a certain sequence S. And we want to get this S back from B. We know that the correct answer is S equals $, and so at the end, we can check whether we indeed get it as the output of the procedure. As explained, first we put B as the first column of a matrix, and then we sort the rows of the matrix. Notice that since each row has only one character so far, many rows are identical up to now. Next, we insert B as the first column of the matrix again, while keeping the second column unchanged. Then we sort the rows of this matrix again. In the same way, we insert B again as a new first column of the matrix and sort the rows, and so on. Until we finally get a matrix with 11 columns, since B contains 11 characters. Now we look at the first row and move the $ symbol to the end, which gives us $, as the output, just as we have expected from the beginning. Now we understand how this procedure works. But why does it work? The answer is that after we have inserted B as the first column and sort the matrix, we get exactly the first column of the sorted rotation matrix. Then when we insert B as a new first column and resort the matrix, we get exactly the first two columns of the sorted rotation matrix, and so on. In other words, after the ith iteration of the procedure, we get exactly the first I columns of the sorted rotation matrix. In that case, of course, after the nth iteration of the procedure, we get back the whole sorted rotation matrix, and so S can be obtained from it easily. Let's use our example to illustrate. Here we show the sorted rotations of S on the left and the intermediate results of the reconstruction procedure on the right. At the beginning, we insert B as a column of the matrix. As discussed before, since every column of the sorted rotation matrix has the same composition of characters, after sorting this column, the result must be identical to the first column of the sorted rotation matrix. Now, if we insert B again as a new first column, we are actually placing the last column of the sorted rotation matrix before the first column of it. Due to the properties of rotations, each row of this two-column intermediate matrix must be a length 2 subsequence starting from a different position of S. Therefore, after sorting, the matrix will become exactly the first two columns of the sorted rotation matrix, and so on. You may want to spend some time on comparing the sorting result after each step with the first columns of the actual sorted rotation matrix, and everything would become clear. As usual, one big problem of this conceptual method is that it is very slow. In fact, it also requires a lot of space. In the next module, we will introduce the fifth property of the sorted rotations, which can help us get back S from B very efficiently. That property will also help us construct a method for performing text search using BWT.